Hello. The title of the talk is An Algorithm Theory for Conscious Learning. The subtitle is $10 million Problems Solved. Because the time is tight, so I will concentrate on 10 problems and give you intuitive explanations. Conscious learning is necessary because human and for robot that learns will gradually accumulate consciousness. No motor imposition, learning is conscious. No big data, static. Learning is fully autonomous. Imitations are of general purposes. Here is the network, where network has the input is collected scene. We have multiple objects. Then we internal neurons that detect features, both top-down and bottom-up. Then we have concept. Here is location. Here is the type. Here is a group. And if you have single object, you then can have a multiple object. In this case, A and B, then can be grouped as a relationship between an A and B. The first problem solved is image annotation problem. In ImageNet, when you teach the robot or machine, you need to annotate each object using a bounding box, then mark the class label. In this case, steel drum. But you cannot annotate a child retina. To solve this problem, the network needs to top down to select the features or objects, and the selection is based on the competition among the internal neurons. You can also select the concept. Here is A and B. If this one fires, then you have the top-down connections that link two objects. And here two objects are from top-down connections. It disregard the background. Since the motor recurrence problem is that depends on where you turn left or right, what you see isn't different. So next image depends on the current actions. The big data flaw is that the next sensation depends on nothing. It just statically collected all the action already assumed. So all public available data sets are flawed. To resolve this problem, the motor will generate actions. Then depends on action generated, then the next sensed images are different. The motor supervision problem, it's very tedious. You can handhold the child hand, but it's only for course action, like which direction to go. And as the motor of the child is still autonomous, so it's not possible for internal actions by attention. So give example that pay attention to what I'm saying. Pay attention to that car coming towards you. Those are the internal action cannot be supervised. To solve this problem, attention will be represented as a language. Then when you speak a language, the motor neuron corresponding to the meaning of the language will be firing, then use top-down corresponding to the action that's required, including external motors, including language concepts. Sensory calibration. George Stratton famous experiment where he designed a goggle that inverts the word upside down, not this type, this is a more modern type. He showed that human can calibrate upside down sensors interactively and through experience. The entire process takes about 2 weeks. The network can also do that. Lower neuron will not really change much because still detect features, but the higher neurons, like the frontal cortex connection, will be rewired through experience. Inverse kinematics problem, this is the forward kinematics from joint angle. You know the effector, location, and orientation. Inverse kinematics, you can, starting from the end effector position and orientation, you need to solve the inverse kinematics for all the joint angles. But if the arm is redundant, more than 6 degrees freedom, then you have infinite many solutions. Human baby can learn the control by doing pre-reaching and reaching through trial and error. Our network is able to generate actions through partially learned skills and gradually learn the most efficient way to reach objects like A and B. Government-free problem. In our cortex, we have representation of the body skin, but there's no government that controls entire brain. In the network, all the computation of the network is totally distributed. Each neuron compute autonomously, independent of others' computation. All the computations are parallel, but the competition between the neurons allows them to sort out which neuron does what. Closed skull problem, the skull is closed, so during learning, the learner cannot get into the neural network to tune the parameters. So human trainers are not allowed to tune the network parameters. And in our network, all the computation are totally automatically carried out. There's no need to hand tune parameters. The linear control problems. This is a linear controller for something like radio. But if you have a more complex problem, then you end up with linear control problem. But the linear control theory in electrical engineering still a little extension from linear controller theory, and the general control problem for the linear issue is not solvable. The DN solved the linear control problem using a general framework of Turing machine. The control of Turing machine is a final state machine. If output not only the state, but also the output action and tension, then it becomes an FA, and network can approximate any FA in an optimal way. The closed dynamic linearity problem means that if you have more features, if the input, which is the number of pixels dimension increase, then the classification error will decrease. But if you add the dimension of the input, then the performance go down no matter how many features you increase. So number of feature increase will not lead to increase the performance. Our network resolve this problem because each feature has a top-down and bottom-up, and has an early neuron, which is more concrete, and the later neuron has also a bottom-up, top-down input, which is more abstract. So different neuron will detect different contexts, each context corresponding to bottom-up input, top-down input, and a lateral input. The undersample problems. In human learning, especially high activity like language, you need to only give you a few examples to the kids, and the child can generalize very well, especially the language. And Steve Pinker said that this is the language instinct. The DN also solved undersample problem. The main idea is that because the number of sample is very few, and the projections between the later cortex, over here it's a frontal cortex and the motor cortex, very abstract, then the wiring takes place are dynamic, still based on optimality of maximum likelihood. You don't need to have many samples to establish abstract projections. Very much like universal Turing machines, you can learn a role just from a couple of examples. There are other $10 million problems solved. I'm sorry, I don't have time to explain all. In this time frame, I can only explain 10. Then the other 10, I like to just mention them. The distributed versus local representation problems. Both representation exist from more local representations like motor abstract concepts to more distributed representations like features across many pixel locations. The frame problem, it's also called simple grounding problem. The frame problem is in AI concerning the time change through frames. The same concept should translate into other frames. The simple grounding problem in robotics. And the local minima problem, it's solved because the optimality, global optimality going on, there's no local minima problem. The same experience from different random initial guess of the weights will lead to the same network. The abstract problem that has to do with invariance and transfers. Role-like manipulation problem, solved through a complete framework of universal Turing machines. The smooth representation problem, which is useful for growing from a small network to many cells, a large network, and also for brain damage, damaged area need to be repaired by recruiting nearby neurons. So this smooth representation is extremely important. The motivation problem has to do with serotonin, dopamine, acetylcholine, and norepinephrine for pain avoidance, pleasure seeking, uncertainty, and novelty. Global optimality problem will solve the catastrophic memory loss in incremental learning, and it's a maximum likelihood. The auto-programming for general purpose problem is solved because the network is able to learn the complex programming for general purposes that's based on optimal GNSM universal Turing machines. The brain thinking problem, Alan Turing raised it 1950. Can machines think? Yes, based on the model here. Discussions. Overall, it's from 3D to 2D to 3D. The word is 3D. Then the image and motor map is very much 2D. Then it generates actions on through motor map and carry out incrementally, interactively on the fly to 3D. So it's a 3D to 2D, then to 3D, a closed loop. Major advice from this work is without motor imposition and freedom from annotations in images, and no need to supervise motor either. So motor supervision is allowed, but not necessary. It's a paradigm shift in AI. Human-like conscious learning is theoretically sound because the theory and algorithm here. This particular paper is algorithmic theory. And the future has a challenge, which is one major problem that has not been solved. Brain science, brainoid chips that runs at about 100 hertz refresh rate for the sensory frame. Thank you very much.